Okay, ready? Let's see. Tonight I'm going to hold my Q&A, and so I'll give some tips on the homework. Again, anybody's welcome to come. There will definitely be people online who want to communicate in real time, so a big part of it is kind of an online office hour for the folks who are at a distance. But once again, I'm 100% happy for other people to come physically, and you can ask questions as well. So we're still in topic 5, and I think we will be through Wednesday. We do end up spending a fair amount of time on this material because it shows up repeatedly throughout the semester in different forms. So the basic ideas that we're learning about in these initial chapters, and this chapter in particular, the idea of multivariate inference requiring a test statistic, a sampling distribution of that test statistic, and then we can get p-values or confidence regions. We're going to talk about confidence regions on Wednesday. Certainly for the next 2, 3, or 4 chapters, there's going to be a lot of really similar sounding stuff that's very similar to what we're seeing here, just adapted to different problems. Where we're at currently in the notes is slide 15, likelihood ratio tests. I'm not going to spend a whole lot of time on this, but I do want to say some things. As a reminder, let me write down on our whiteboard a random sample of data. We have each of n individuals that were chosen randomly from a target population. And for each one of those individuals, we have an x variable. That could be a univariate variable, or more like our class, a multivariate vector. If we assume a probability distribution that gave rise to our data, if we say our n measurements of water acidity follow a normal distribution with a mean mu and a standard deviation sigma, if we do that, then we can do stuff called likelihood-based modeling, likelihood-based inference. So if we assume a probability distribution, call it f of x, because it's a probability distribution for the x's that we're observing, whether they're univariate or multivariate. And I'll put a little theta underneath as a subscript, as in there's a potentially a vector of unknown parameters for this distribution. Any probability distribution that is parametric, which is most of them, normal, t, gamma, all that stuff, they have parameters, 1 or 2 or 3 parameters that if you tell me the value of those parameters, it completely determines the shape of the normal or the chi-square or whatever. The normal distribution, for example, has 2 parameters, the mean and the standard deviation. So just generally, suppose we are willing to assume that a particular probability distribution applies in the population we're studying. So the n individuals that we sampled from that population can be viewed as n draws from this distribution. If we do that, then there's this quantity called the likelihood. And the likelihood is viewed as a function of the unknown parameters. It's going to quantify, you tell me a potential choice for theta. What do you think the mean and the standard deviation are? And I can compute a quantification of how likely it would have been to see our data if those parameters were the right ones. If the average pH in the lake is 1.1, it'd be really unlikely for us to see data that was all 8.4. So we can quantify, using probability, the, quote, likelihood of observing data like we saw for any choice of the parameters. Once we've done that, then a very sensible way to estimate those parameters is to choose the value of theta that maximizes that quantity. That's called maximum likelihood. So a likelihood, in this context, is just the product of the PDF evaluated at each of our observed variables. If you think back to Stats 101, if two random variables are independent of each other, statistically independent, then the joint probability of the one and the other is equal to the product of their individual probabilities. If you have independence, you can multiply probabilities, basically, to get a joint probability. The likelihood is kind of a joint probability. What's the likelihood? How likely? Well, how probable is it to see x1, x2, dot, 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 all the way through xn? So it's a joint probability thing given a particular choice of theta. So that's where this product comes from. It's like we're saying, what's the joint probability of seeing our data for that choice of theta? It's not exactly a probability, though. You have to be a little bit careful with your language with likelihoods. It's like a probability. It quantifies the likelihood of seeing your data. So then with a likelihood, maximum likelihood, would say my best estimate, according to the likelihood theory, is the value that maximizes the likelihood. I choose as my estimate of the mean and the standard deviation the pair, mu standard deviation estimates, that make the likelihood function biggest. And then what's also nice is we know a lot. Let me rewrite that. We know a lot about sampling distributions of MLEs. An estimator that you get by maximizing the likelihood is called a maximum likelihood estimator, or MLE. So using this framework of saying, I want to choose my estimates to kind of best fit the data I saw, to make it so that I'd be most likely to see the data I saw. That's a choice that we make as like a principle for moving forward with estimate and inference. Turns out to be a good one, not least of which because the estimate is just an optimization problem. Maximize the likelihood function with respect to theta. And especially because we know a lot about the sampling distributions of the resulting estimates. Inference, p-values and confidence intervals, it's all about estimating parameters and then using sampling distributions of your estimates to extract confidence statements about I either accept or don't accept this hypothesis, or I think the true value of mu is in this region here. So that's meant to be an aside. I think everybody who has a modern statistics class nowadays should know what a likelihood is and what maximum likelihood is. Just to add one little useful conceptual insight, when you're familiar with the idea of Bayes' theorem, you're familiar maybe with Bayesian statistics. So there are two camps of statistics. There's the frequentist camp and there's the Bayesian camp. And literally, different people view probabilistic problems differently. They have a different way of thinking about it. Likelihood is frequentist thinking. Let me choose my estimate to best match my data. Bayesian thinking actually treats the unknown parameters as random themselves and postulates a distribution for the parameters. So if we had data on acid in the lake, and we could say the distribution of the pH in the lake is normal with such and such mean and standard deviation, then if you wanted to know for a given sample of the lake, what's a likely range of pH values I'm going to get, you could just go to the distribution and get an arbitrary interval that you want. I don't have time to go very much further into Bayesian stuff, but let me just note one thing. Bayes is related to likelihoods. Specifically, we say what's called the posterior probability distribution for theta is proportional to, there's a constant involved, but conceptually we can ignore it, is proportional to the likelihood of theta times another probability that's called your prior probability distribution. Bayes' theorem, Bayesian statistics, takes the likelihood, which is like a purely data-based assessment, and it blends it with your prior beliefs or prior convictions. If you're the sheriff of a town and somebody was arrested for murder, and you just know this person did it, you have strong belief, prior belief heading into the trial that this person did it. But then new data emerges, DNA evidence, that excludes this person with high probability. The likelihood, based on the data, does not support guilt. You have prior beliefs, you have data, how do you put them together in a sensible way? Bayesian statistics is that kind of thing. So you base your inference on a posterior distribution. Let me see what data we have. Here's what I believe going in based on previous research or existing studies or stuff. And then I'm going to use this kind of principled mathematical way to blend them together and update my beliefs. Okay. So all of that to introduce this chunk of the slides, likelihood ratio tests. It's the same use of the word likelihood. I won't test you on the mathematical theory here, so just follow along conceptually. If we're dealing with likelihoods, we use the capital L of theta generally to indicate a likelihood for a distribution that has parameter vector theta. Then there is kind of an optimal way to do a hypothesis test. If you have a parametric setup where you say, I think the distribution of my data is such and such, normal, whatever, then you can play likelihood games. And within the likelihood framework, the best way you can test a particular hypothesis is with likelihood ratio tests. So people thought for decades, before the advent of computers in particular, what's the sampling distribution of the ANOVA F statistic? And they had to figure those things out analytically. So while figuring that type of thing out, you end up asking, well, here's two valid tests of the same hypothesis. Which one's better? Well, you would call it better if it had better operating characteristics, like had higher power than the other test. For a given type 1 error rate, if it has a higher power, that's a better test. So in terms of quantifying the goodness of tests, likelihood ratio tests are optimal in certain situations. For parametric problems, likelihood ratio tests are a great way to proceed. And many of the tests that you know by name, like t-tests, f-tests, can be motivated as a likelihood ratio test. So here's the definition. If we have data, x1 through xn, each one of those is a vector, and they come from some probability distribution in the population. Could be multivariate normal, for example. But it comes from some distribution, and that distribution has parameters that we're going to generically call theta. That could be the vector of a mean and a standard deviation. Or it could be a bunch of means and a bunch of standard deviations and a bunch of covariances in the multivariate normal case. So it's just like on the whiteboard that I wrote down. We have data that came from some distribution f theta. Let L of theta be the likelihood function. So it's the product of the PDFs, the product of the densities evaluated at the observations. Theta takes values in some range. If we're talking about standard deviation, for example, it has to be bigger than 0, but it can be up to infinity. That's a range of possible values. So we use in the notes capital theta to indicate the total range for the different parameters. Okay, so here's where it comes to inference stuff. Suppose you want to do a test, a hypothesis test. I want to make a formal decision based on data about whether a particular parameter takes a value or does not. So here's a hypothesis test setup. Null hypothesis is that theta equals something that we specify. Theta 0 just indicates a particular theta that we wrote down. I think the pH is 5.2 and the standard deviation is 1.8. Then the optimal test in many cases is this test with this test statistic. Doing hypothesis tests, you have to compute a test statistic. That's something that quantifies the evidence against the null hypothesis. So the likelihood ratio statistic is literally a ratio of likelihoods. In particular, it's the ratio of the maximized likelihoods. The numerator is go get the likelihood, maximize the likelihood by considering all theta choices that have been restricted to be in accordance with the null hypothesis. Whereas the denominator maximizes the likelihood without restriction. The denominator is just maximum likelihood. Go find the theta that maximizes this likelihood. The numerator is just like that, except theta is restricted on the values it can take. Ultimately, you compute two likelihoods. It's like the best fitting likelihood under the null divided by the best fitting likelihood under the unrestricted case. Test statistic. And then we will reject the null if this test statistic is sufficiently small. Why small? The statistic is a ratio. It's the ratio of the best likelihood under the null to the best likelihood unrestricted. So if the null hypothesis is not true, then the numerator and the denominator can be expected to be pretty different. And in particular, the numerator will be less than the denominator because the denominator is the best across all possible thetas. The numerator is restricted. So we expect evidence against the null hypothesis to look like small lambdas. Just as an aside, test statistics, we're always computing them to, again, quantify the evidence against the null. But the directionality depends on the specifics. Some test statistics, you want to see big, extreme positive or negative values. Others, like this one, it makes sense to do small values. So you have to keep that straight. This is a general form for a really good hypothesis test. If you have a parametric model, you write down a probability distribution for your population, then you can do maximum likelihood to get a likelihood ratio test. That's your statistic. Instead of a T statistic or an F statistic, it's this lambda statistic. And then what's handy, I mentioned on the whiteboard, we like maximum likelihood because we know a lot about the sampling distributions that come about through the theory. So here's one example of how we know good stuff mathematically. That lambda statistic was a ratio of likelihoods. It turns out mathematically that if you transform this to be -2 times the log of lambda, so -2 times the log likelihood ratio, that has a known distribution. It's a chi-square. So that's a super general result. If you can write down a likelihood, then you can compute lambda to test any hypothesis, And you can compute a p-value by going to that distribution, the chi-square. That gives rise to t-tests, ANOVA f-tests, lots of stuff that we know and love in other situations, the general theory of maximum likelihood. And then really quickly, I'll go through this. Again, I'm not going to test you on the math, but this is just showing in the multivariate normal case, what does this likelihood ratio stuff look like? This slide is just introducing the multivariate normal and rewriting it in a convenient way. But we're starting with, up at the top, multivariate normal probability. So our likelihood is a function of the vector mu and the covariance matrix capital sigma. Beyond that, it's just likelihoods, and we can estimate things by maximizing the function. It turns out that you can see the textbook for all the gory details, but it turns out that in the multivariate normal case, lambda, the ratio of the maximized likelihoods, takes a form of this. This happens to equal a ratio of the determinants of covariance matrices raised to the n over 2. And it turns out further that we can relate that quantity back to the t-squared statistic. So lambda can be shown to be equal to this. And using really some basic algebra, if you put lambda in a transformation of this form, then you completely get back t-squared. So all of that to say, maximum likelihood is a general framework that shows up an awful lot in different names. Here we're seeing t-squared stuff. That's motivated by, or can be motivated by, likelihood-based arguments. Okay, I want to spend some time on this. This will be a little more applied, I think, than all the theory that just preceded this. When doing inference, sampling distributions are the key. So go back to my whiteboard. We have a population. This is every single postmenopausal woman in the US. And in the population, there are parameters, theta. So we might say this is a mean and a standard deviation, for example. Because we can't assay or interview the entire population, it's not practical, we don't have time or resources, we take a random sample. So a representative subset of the population who we identify and are going to assay. Within the sample, or based on the sample, we get sample estimates of our parameters. So for example, we might get X bar and S, estimated sample mean and the sample standard deviation. The population parameters are mu and sigma. These are parameters. So now, in order to do inference, which is take my sample data and use it to make confident statements about the population parameters. You can never fully represent the population unless you get the whole population. I've used an example in Stat 101 of a lake full of fish. Suppose there's a big lake and there's a bunch of fish swimming around, and you want to know what's the average weight of the fish in the lake. That's your parameter, average weight of all the fish in the lake. But it's a huge lake and there's hundreds of thousands of fish. You could answer the problem perfectly by draining the entire lake and weighing every single fish. Then there is no uncertainty. The average weight is such and such. In practice, you can't do that, so you take a sample. Maybe you go out and catch 100 fish from all over the lake. So now you have a sample average weight, and you could also compute a sample standard deviation. But in order to do a hypothesis test and compute a p-value, or to construct a confidence interval. Like I'd like to say in that fish case, I don't know what the overall average is because I didn't drain the whole lake, but I can say I'm, quote, 95% confident that the average is between 11.1 ounces and 14.2. So inference, by which I mean p-values and confidence regions, requires a sampling distribution. So I need to know, for example, what is the sampling distribution of X bar. If I want to do inference, make a confident statement about the population mean, my natural estimate is X bar. That's a sample statistic, and because my data are random, the sample statistic is random and has a probability distribution. We give it a special name, sampling distribution. P-values and confidence intervals come directly from the sampling distribution of my statistic. So what I'm about to talk about in the notes takes us a little, takes us away somewhat from our reliance so far on a specific probability model. I've been talking up likelihood and maximum likelihood and likelihood ratio tests. They're great if you're willing to postulate a probability distribution. I think my pH measurements follow a normal distribution. That's an assumption and may well not be true. So there are other techniques that don't require such a strong parametric assumption. Okay? So in this case, suppose we wanted to make inference on a mean. One way to proceed would be in a parametric way and say the population distribution is normal, and therefore I can do t-based stuff. An alternative way would be to say I'm not going to specify anything about the probability distribution in the population. I don't know what it was. I don't want to make assumptions. I get data. I compute my statistics. Now I want to do inference, but I need a sampling distribution of my statistics. But I haven't specified a likelihood. So it turns out that there are resampling techniques that allow you to kind of empirically, not analytically, but empirically approximate the sampling distribution of arbitrary statistics. So in this case, we want to do inference on X bar. If we were willing to assume that my data come from a normal distribution, then it's Stat 101 stuff. It's t-tests, t-based confidence intervals. If we weren't willing to make that assumption, then we would be left with this bottom line, and we'd have to figure out an alternative way forward. So there is a resampling technique. Basically, you take your data that you observed, the 100 fish from my lake, and you take a random sample from that data. And then you treat that random sample as if it's another random sample from the lake. So here's my lake full of fish. I'm going to go out and randomly catch 100 fish. That's my one sample. But if we were to go out and do it again, here's another 100 fish and another 100 fish. If we did that lots and lots of times, we would get a different sample average each time. And then if you drew a histogram of all those sample averages, that would basically be the sampling distribution of X bar. So we try with this bootstrap idea, resampling-based idea, we try to mimic that repeated sampling. If we were to each go take a sample of size 100 and get an X bar, then we could make a histogram of the sampling distribution of X bar. It turns out that there's a trick that allows you to basically do that without having to repeatedly take samples from the population. So you go catch 100 fish once, and then you use a technique called the bootstrap, which is a resampling technique, and you're able to approximate the sampling distribution. It's kind of a magic thing. So I think it might be easiest if I write it on the whiteboard first. So we're going to talk about here the bootstrap. Scratch that. Let me go to the slides. I think I probably said it about as good as I can in the slides. So slide 20, I think. The idea of the bootstrap. We have observed a data set, x1, x2, ... xn. But we're not specifying its distribution. All we have is the data. I'm going to go to the whiteboard. That'll be better, I think. So we have data, x1, x2, xn. And they are a random sample, independent and identically distributed from some distribution that we're not going to specify. And suppose we want to do inference on the population mean. So t-test and t-based confidence intervals, that type of stuff. I just want to estimate a population mean. Here's how you do the bootstrap. Step 1 is to compute x bar and s. Just the usual sample statistics that you get from these data. My mean, my standard deviation. Then is an iterative looping procedure. So for each of capital B times, capital B is the number of bootstrap resamplings we're going to do. There's not a magic number for what it needs to be, but the more the merrier generally. Thousands would be great. 1,000, 2,000. For each of B times, create x1 superscript b, x2 superscript b, ... xn superscript b by sampling with replacement. From the original data that you observed. So I have my 100 fish weights, and my bootstrap sample right here is going to be, let's sample with replacement from my 100 fish. That means I could get fish number 1 and fish number 1 again and not get fish number 8. I'm just sampling with replacement. Every single time I take a fish, I put it back and it can be taken again. After you've done that, you now have a new pile of 100 fish measurements. They were all taken from your original ones, but for practical purposes, we're able to treat it as if it's a new sample of 100 fish. So what we would do with the new sample of 100 fish is compute x bar superscript b and s superscript b. You repeat that lots of times. So at the end of step 2, if capital B was 1,000, say, you would have 1,000 x bars and 1,000 s's. So then step 3, treat the empirical distribution, and all I mean by that is histogram. Not a curve, but a histogram of your capital B sample statistics. Treat the empirical distributions of the capital B sample means and SDs as if they were the sampling distributions. The idea then is when you have data and you're not comfy with making a parametric assumption, you can do inference by computing a statistic that makes sense. In this case, I wanted to estimate the population mean mu. So a natural statistic to compute is the sample mean, x bar. If I want to use x bar as the basis of inference, then I need the sampling distribution of x bar. The bootstrap is a general way to approximate the sampling distribution of whatever statistic you want. You compute your statistic on the original data, step 1. Step 2 is iterative, and for each of a bunch of times, you create kind of a new pretend sample by sampling with replacement. And with that new pretend sample, you compute your statistics again and store them. Yes?
So for the second step, like the iterative step, what is the actual reality? Like, if I'm doing the calculation for the fish population, like for 100 fishes, and like if I take b equal to 1,000 times, I do the iterative, then 1,000 into 100. That is the number of fish that I have to catch, and I can replace. And I can catch and take the data from there and replace. Is it so?
Not sure I understood all of that, but you would catch 100 fish, and then you would apply this to your 100 fish, and you would have an approximation of the real sampling distribution of x bar, which means you could do confidence interval or a hypothesis test. So it's as if you were doing a t-test. With a t-test, you assume normality of the population, and given that, step 3, I know what the sampling distribution is. It's t. So I can just use my 100 fish and apply a t-based result. Here, we don't want to make the assumption of normality or any assumption like that. So the trick is the resampling loop. But it then makes it as though you knew the actual sampling distribution.
Catch one fish, then I will replace that thing. Then again I'll catch one fish.
So you catch 100 fish at the very beginning. Caught a fish, he goes in your barrel. Caught another one, goes in your barrel. There's no replacing as you're collecting your original sample. And then suppose you write down the weights of all the fish and put them into a hat. Then you grab in, get one, and that's the weight. I'm going to write it down in my Excel spreadsheet. I'm going to put that back and do again. So the with replacement thing only happens in the bootstrap stuff. So I wanted to get to some code. But I think we need to do this slide first before we do the code. So everything on the whiteboard holds generally. It was a pretty general statement of the bootstrap. There are some details, depending on whether you're wanting a p-value to support a hypothesis test or a confidence region. Bootstrap is easiest to use for confidence regions because all you do is what I described on the whiteboard. You just sample with replacement, compute your x bar values, and store them. So for example, let me come back over here. In the same context where we have the x1 through xn, and we did the bootstrap, capital B times. Here's, let's say, the histogram of my capital B x bars. They're centered at some midpoint, and they're spread out. That's just a sample histogram of my 1,000, say, X bars. Then it turns out a valid way to construct a confidence interval. If you come over in this direction and the other to the point that captures 95% of the sampling distribution, this is A and this is B, then A, B is an approximate 95% confidence interval for mu. So after you do the bootstrap, you have your big pile of capital B statistics, and a super simple way to get a confidence interval for whatever parameter those statistics estimate is the inner 95% of the histogram that you saw. In the t-based setting, we would do x bar plus or minus 2 times s over the square root of n. This is kind of replicating that. In fact, let me see if I can do this off the cuff. Let me show you an example of this in action. So my data, we're going to take a sample of 100 fish from the lake. In the lake, we're playing pretend, so I'm going to say the mean is 11 and the standard deviation is 1. Just totally making that up. There's a fish full of lake, or a lake full of fish. The population average weight is 11. SD is 1. I'm going to take a sample of size 100. So let's assume normality for the sake of illustration. Give me 100 draws from the normal distribution with my mean and standard deviation. Then a t-based 95% confidence interval for mu would be, let me write down my sample statistic. We have 100 fish. The sample mean x bar is just the mean of my 100 fish. And the sample standard deviation is just the sample SD of my data. Those are two statistics. X bar in particular, I could use to estimate mu. So I have an estimate. If only I had a sampling distribution for x bar, I could do inference. For example, a confidence interval. The t-based 95% confidence interval is x bar plus or minus, and this is just a quick way to say plus or minus, x bar plus or minus basically 2, close 1.96, times s divided by the square root of n. And that's a valid confidence interval in this setting because I am playing pretend and I simulated directly from the normal population. So I could use t-based stuff. And then here's what the bootstrap would look like. Suppose I didn't know that my data were normally distributed, or I didn't believe that they were. Then for each of a bunch of times, let's do 2,500 times, I'm going to do a loop for b in 1 to capital B. So for each of capital B times, create a bootstrap sample by sampling with replacement from my original sample. Sample function does what it sounds like it does. It'll randomly take elements from the first argument. And then by saying replace equal true, it will replace every time I do it. So this samples with replacement, does what the bootstrap needs it to do. I now have a new 100, n equal 100 sample. And now I can just compute my statistic and store it. So I'm going to store it in a vector. So the bth element of this new vector, oops, This needs to be x underscore b. And I'm going to create up here an empty container. Multiple ways to do that. I'm just going to say numeric b. That creates an empty vector of length capital B. So inside the loop, I'm going to sample with replacement to get a new kind of pseudo 100 fish. And I'm going to store the sample average of those bootstrapped fish. Then if I make a histogram of those 2,500 X bars, I should be able to overlay. I won't do that. Then a 95% confidence interval. Let's go ahead and do the histogram, X, B, vec. And let's compute the, if I want to capture, I want to pick A and B, endpoints of an interval. I want to pick those so that they capture the inner 95% of this distribution. One way to quantify that would be that A is the 2.5th percentile and B is the 97.5th percentile. The 2.5th percentile puts 2.5% of the probability to its left. The 97.5th percentile puts 2.5% of the probability to its right. So in total, there's 5% in the tails. So those are the two numbers that I want. Let me just show you it. We're running out of time. There's a quantile function. Make sure I get the syntax right. So there's a quantile function. I can say, give me the quantiles of this vector. And the quantiles I want are the 0.025th and the 0.975th. Okay, I'm going to run all of this. Hopefully, we'll have a nice punchline. Okay. All right. Using the t-based method, the usual Stat 101 method to get a 95% confidence interval, we got an interval from 10.67 to 11.02. And I can legitimately say I'm 95% confident that that interval contains the truth. What we specifically mean about that is a little tricky, and we'll play with that on Wednesday and when we talk about confidence regions. But we can say with some jargon, 95% confident that that interval contains the truth. We know what the truth is, by the way, in this example, because we're playing pretend. It's 11. Go ahead.
This interval will also change from my sample to your sample?
Yes. A confidence interval is itself an estimate. If I got a sample of 100 fish, I'd have an estimated confidence interval. If you did it, you'd get a different one. What we can say about 95% confidence intervals is that while mine will differ from yours just due to random variation, we can say that we expect 95% of all 95% confidence intervals to be correct, to actually contain what they're estimating. I may have gotten unlucky with my 100 fish. So that's the parametric 95% confidence interval. And here is a bootstrap 95% confidence interval, 10.67 to 11.01, almost exactly the same. And what's really cool is we didn't say anything in that bootstrap stuff about normal distribution or t-distribution. We just used the data in a non-parametric way to get an estimated sampling distribution. And then inference is all about sampling distributions. For example, give me a confidence interval. That translates to give me a couple of percentiles from the sampling distribution. I'll talk to you on Wednesday about p-values. They are a little bit different. Yeah, okay, so lots of material. I hope it was helpful. See you Wednesday. I will have the Q&A tonight, and it's